Hi, everyone. Thanks for joining the Protocol Labs Research Seminar Series. Today's speaker is Naomi Ephraim. Naomi is a fifth-year computer science PhD student at Cornell University. Her advisor is Professor Raphael Pass, and her research interests are in theoretical cryptography. She's going to be talking today about non-malleable time lock puzzles and their applications. Naomi, go ahead.
Thanks for the introduction. So I'll be talking about non-malleable time lock puzzles. This is joint work with Cody Freitag, Elon Komorgotsky, and Raphael Pass. And if anyone has any questions during the talk, please feel free to interrupt me. So I want to start with this topic of generating randomness. So we have n people, and let's say they have access to a public bulletin board. And the goal is to flip an unbiased coin in a way that they can all be convinced that it was generated in an honest way. And as you can imagine, this is a really fundamental task, right? It's especially in blockchains, for electing leaders, or for digital lotteries or online games. So this has a lot of applications. And so it's really important to do this in a way where we sort of minimize trust and minimize our assumptions. So for now, let's just focus on the two-party setting. So we have Alice and Bob, and they want to flip an unbiased coin. So just as a sanity check, just to get it out of the way, the first thing you might think to do here would just be, let Alice flip a coin and post it on the board and just say that's the output. But clearly this doesn't work, because then you have to trust Alice, right? You have to trust that she flipped an unbiased coin, which we don't want to do. We don't know her motives, so this doesn't work. So a sort of a better solution is to have everyone give some input towards the output of the protocol. So to have Bob also flip a coin, let's say he gets B2, post it on the board, and then combine their outputs using a suitable function. For example, XOR is a good function to set the output to be the XOR of B1 and B2. And the reason for this is because at least if Alice and Bob both act honestly, we'll be XORing two uniformly random and independent bits, so the output will be unbiased. So this seems better, but of course, this is just completely insecure. So if Bob here is the adversary, what we can notice is that he just completely controls the output, because he sees Alice's input before he has to post his output. So he can just look at B1 and pick B2 based on B1 exactly to control what B1 XOR B2 is going to be. So still, this does not work. So one approach that has been proposed recently to fix this is to use these so-called slow functions or delay functions. And how this works is, instead of computing the output as the XOR, you use this function f, which takes longer than the protocol to compute. So the idea here is that Bob, he'll see B1 before he has to choose B2, but he won't be able to compute f on B1 and B2 during the protocol. So he won't be able to test how B2 will influence the output. So this sort of fixes the problem from before, because before he could just compute XOR, but here he can't test how his bit will influence the output. So he doesn't have control over the output like he did before. But the main problem with this approach is that the honest players also need to compute f to get the output. They're sort of being punished for the existence of malicious players. And also, this approach usually requires setup, so that's another source of trust, and we don't really want to have that. So in this work, what we've been looking at is how we can get security against parties which deviate arbitrarily from the protocol, but keep the practical efficiency that we want. So towards doing that, we're going to need a little bit more crypto than before. So next, I want to look at this really common approach towards coin flipping. So this is called the commit and reveal paradigm. And the main idea here is that both parties should commit themselves to their inputs before seeing the other person's input. So Alice and Bob, as before, pick random bits, and then they commit to it using a cryptographic commitment. So this commitment is going to hide the input and also bind them to that value. So they won't be able to change the value once they've committed to it. So they post these commitments on the bulletin board, then subsequently open them up. And the output is going to be the same as before. And additionally, they just need to check that each other's opening is consistent with the commitment. So Alice will check that B2 is indeed the value inside this blue envelope here. And this is better because Bob has to pick B2 and commit to it before seeing B1. And again, just as a sanity check, we still have that if everyone is honest, the output will be unbiased. This is sort of for the same reason as before. But we don't want to only have security in the case where everyone is honest. We really want security against malicious adversaries that behave arbitrarily. So if you think about this, sort of like a really easy attack to do here, which doesn't depend on the commitment, like you don't have to do anything fancy, is just to abort early. So again, if Bob is the adversary, what he can do is he can see Alice's commitment, send his own commitment, see her opening, and then just refuse to reveal his opening based on what she said. So we can't just ignore his input if he chooses to abort, because then he's essentially choosing whether or not he prefers the output to be B1 or B1 XOR B2. So we're kind of back to square one here. And this is actually a famous impossibility result, which says that an adversary that just aborts can bias the output of this protocol. One approach to circumvent this has been to use these timed primitives to replace commitments. And that's what we do in this work. So next, I'm going to tell you a specific time primitive. It's called time log puzzles, and I'm going to tell you how we use it to fix this protocol. So a time log puzzle is a mechanism to encrypt a message to the future. This was introduced by Rebus, Shamir, and Wagner in '96. And more formally, what it does is, given some message S, it allows you to generate a puzzle for S, which I'll denote like this. So this puzzle, it hides S up until time T. So there's a solve algorithm that can recover S from the puzzle in time T. And there are two properties that we need. So the first thing we want is that, or the first thing that time log puzzles guarantee, is that puzzle generation should be efficient. So even no matter what this parameter T is, no matter what the difficulty of the puzzle is, it should be really quick to generate a puzzle. And the second property is that solving shouldn't be able to be sped up. And in particular, this should hold even against adversaries that use parallel strategies, which is really important if you think of blockchain applications where people do have massive parallelism. We really want security against that. So that's what a time log puzzle is. And the most well-known construction is based on the repeated squaring assumption. I'm going to define this a little bit later, but it basically says repeated squaring in a group of unknown order cannot be sped up. And there are also other constructions from stronger assumptions. And sort of the takeaway, if you think of what a time log puzzle is, a good way to think about it is that it's a commitment, which is, it binds you to this value S, but it's only hiding until time T. So it's sort of a weaker version of a commitment. Okay, so let's go back to coin flipping. So what we're going to do is replace the commitments that we had before with a time log puzzle. So again, Alice and Bob are going to flip 2 random coins. They're going to post now time log puzzles to the coins on the bulletin board and reveal their openings. But then the key point here is that if Bob refuses to reveal, we can just solve his puzzle in time T. And T will be a parameter of this protocol, which we can set to be whatever we need for our application. So the idea here is that, the aborting attack from before, it doesn't work because we can just solve any puzzle that we need to solve that was unopened during the protocol. And the other point that I want to make here is that the resulting protocol has what we call optimistic efficiency. So if nobody aborts during the protocol, so if everyone is honest, we don't lose anything. We'll just be running this super efficient protocol. But then if someone does abort or act maliciously, then we have to deal with it and solve this puzzle. So, okay. So that gives us security against adversaries that abort. But we want security against fully malicious adversaries. So, okay, so if you think about it, sort of the only attack remaining if the adversary is not going to abort is to sample B2 dishonestly. Because if you think about it, Alice is honest here, so B1 is uniformly random. So as long as B1 and B2 are independent, this output is going to be unbiased. So let's see what the adversary can do to pick B2 in a way that depends on B1. So let's look at this point in the protocol where Alice has posted her puzzle and the adversary is thinking what he should do. So by the security of time lock puzzles, he doesn't know this underlying value, right? It's completely hidden from him because the protocol only runs for time t, so he can't break this puzzle. So he can't choose B2 just directly based on B1. But he still has this puzzle, right? Ideally, we'd want B1 to be completely independent of his view, but it's not. He sees this puzzle. So the attack we need to prevent against is him using the puzzle to create one for a related value. So like a trivial way to do this is just to copy the puzzle, right? If he sees this puzzle and then copies it, that's a trivial way to create a puzzle for a related value. But we can just see if he does that and disallow it. But in general, there might be more complex attacks. For example, suppose that given a puzzle of B1, it's possible to flip all the bits in the puzzle without solving it. This wouldn't break the security of the time lock puzzle because you don't need to know the underlying value necessarily to do this. But if you could do this, then the output would be completely biased. And it turns out that in the standard construction of time lock puzzles, this exact attack is completely doable. So, so more generally, we really need to prevent all possible ways to correlate B1 and B2. And this area of research is called non-malleability. It's been studied in many contexts. So in this work, what we do is we construct non-malleable time lock puzzles, which exactly prevent against this and give secure coin flipping. Next, I'm going to tell you a little bit more about our results. So the first thing that we show is that given any time lock puzzle, we can make it non-malleable. So we can fix the attack from the previous slide. And what I want to highlight here is that our construction, it's in the random oracle model. It has no trusted setup, and it's really, really efficient, at least if you instantiate this time lock puzzle with the standard RSW time lock puzzle. So that's good. And we also get some stronger notions of non-malleability, but I'm going to talk about those a little bit later. But they're going to be crucial to getting coin flipping for n people rather than just 2 people. And lastly, we get the following applications to multi-party coin flipping. So first of all, our protocol is going to be fair. So no malicious party who deviates arbitrarily from the protocol will be able to bias the output, even if they control all but one of the parties. Additionally, if everyone is honest, we won't have any, solving of the puzzles or any slow phase. When everyone is honest, we get just a efficient 2-round protocol. And lastly, we get this property of public verifiability, which essentially means that no matter what happens during the protocol, someone aborts, someone has to solve a puzzle. In the end of the day, the output will be able to be efficiently verified, by anyone who comes later to see what the output was. So we showed this protocol based on the repeated scoring assumption that I mentioned earlier. And I want to emphasize that these are the first protocols satisfying these properties. So next, I'm just going to tell you what this repeated squaring assumption is. So this theorem will hopefully make a little bit more sense. So the repeated squaring assumption says the following. So let n be a product of two primes, or more generally, just take any group of unknown order and sample G from that group. The assumption says that the fastest way to compute G to the 2 to the t, so to square G t times, is to square G t times. So to go from G to G to the 2 to the t, the fastest way to do it is just iterative squaring. So compute G squared and then G to the fourth and so on. And this assumption has been studied and used for over 20 years, and there are no known ways to significantly speed up squaring. So, repeated squaring. So, so if you believe this assumption, it means that sort of however fast you do a single squaring, the amount of time it's going to take you to do t squarings, at least for sufficiently large t, is going to be t times the time to do a single squaring. And this assumption has been used for many applications like verifiable delay functions and randomness beacons and others, and also gives the construction of a time lock puzzle. The first one is essentially just repeatedly squaring t times and then adding the value s that you want to generate a puzzle for. So this is sort of a fundamental assumption in this area of time lock puzzles. Yeah, so does anyone have any questions? This is like a good time if anyone has any questions. Okay.
There's a question in the chat, and
sorry.
So it's
it was a very general question because I was not sure if time lock puzzles or if verifiable delay functions were a type of time lock puzzle, because I was not sure if the definition would be that you have to actually lock something that you know. But like, I guess I can now just answer it, because if a verifiable delay function is an application of a time lock puzzle, then effectively you don't need to know the value before you lock it, correct? You just need to reveal it in the future.
So for time lock puzzles, they are specific to knowing this value before you do it. Here I was more saying that verifiable delay functions are an application of this assumption. So yeah, the main difference between verifiable delay functions and time lock puzzles is that, first of all, verifiable delay functions are verifiable. They're not only delay functions. And the second one is really about knowing this value s before that you're going to encode, because the point with a verifiable delay function, you sample an input and then it takes t time to compute the output. But in a time lock puzzle, you sample really quickly a puzzle for a specific value. So it is a little bit different, but they're obviously very related. They both have to do with delay, and they both use the same type of assumptions. So yeah, great question. Any other questions?
You.
I guess on the repeated squaring, are you doing this in a finite field or over full integers? Because presumably the place where this bound happens is if you have a modulo in there, and eventually you will have some weirdness, right?
Yeah, so typically this assumption is made just in any group of unknown order. So most generally it's in RSA group. It's used in RSA groups, right. Which is why I wrote here just an RSA group. But I think it would be reasonable. Like basically, there are papers showing that if you know the order, this assumption is broken, and if you can factor this is broken. So because if you can factor, you can compute 2 to the t mod the order of the group. So in general, you need a group of unknown order.
Is there also something where even if it's unknown, if your T is large with respect to that unknown order, and you'll just be able to notice patterns of repetition? So you probably also have some expectation of T versus the size of the group.
I'm not aware of anything like that. What you do need is that T should be, for example, here, smaller than the time to factor, because if it's not meaningful to say you can't speed it up if you're running for the amount of time it would take you to factor n. But I'm not aware of anything that does what you're saying, but it might exist. Yeah, and there also have to be lower bounds on T. Like obviously for very small, like squaring once or twice, like you need at least some significantly large enough T. Thanks. Okay, so next what I'm going to do is tell you the plan for the rest of the talk. So okay, so what I plan to do next is define non-malleability a little bit more formally. Then I'm going to tell you how we get non-malleable time lock puzzles from plain time lock puzzles. And finally, I'm going to tell you how we get our coin flipping protocol for our multi-party protocol with all the properties that I mentioned before. So non-malleability. So non-malleability sort of characterizes what a man-in-the-middle adversary can do. So we have here Alice, who's trying to send a time lock puzzle to Bob. And the adversary here is going to intercept this puzzle, change it to something else, and send it to Bob. So let's say Alice sends a puzzle for S, and the adversary intercepts it and changes it into a puzzle for S prime. What non-malleability says is that S and S prime are not related. So no adversary can do this in a way that makes S and S prime be related. And there are a few caveats. So similarly to the protocol that I was saying before, the adversary he's not allowed to just copy this puzzle. Of course, that's a valid mauling attack. It makes the two puzzles related, but we can detect it and just replace his output with a dummy value if that's the attack. And the second thing here is that specifically to the case of time lock puzzles, if you set the timing parameter T, to be, not too large, then if you consider efficient adversaries, they could actually solve the puzzle and then just change the underlying value. So it's necessary here to restrict to adversaries that run in time smaller than the time to solve the puzzles. So in general, in this work, we're looking at adversaries that run in time T, clearly that's necessary here. So that's a definition of non-malleability. So next I'm going to tell you how we actually achieve it. So our transformation to get a non-malleable time lock puzzle starts with just any time lock puzzle and access to a random oracle. So what we're going to do, given some message S that we want to encode a puzzle for and some randomness R, first what we're going to do is to query the random oracle on S and R. So we're going to get some randomness which depends on S and R. And then we're going to generate a puzzle for S and R using this randomness. So it's really simple, but it's also circular. So pictorially, what we're doing, we're taking S and R, we're generating randomness using it, and then we're using that to the two of them together to encode a puzzle. So I'm going to denote here this a puzzle for SR with randomness O of SR. I'm going to denote like this. So this will be the final puzzle in our scheme. And to solve this, what you do is you just solve the underlying puzzle in time T, and then you can actually check that the puzzle you got is indeed the puzzle for S with randomness R. And sort of this circularity flavor that we have here, where we're generating a puzzle with randomness that depends on the puzzle, that is going to be really crucial for getting non-malleability. Let me tell you just a little bit of intuition on why we actually get non-malleability. So we have an adversary, receives a puzzle for S, and his goal is to generate one for a related value, S prime, right? That's the non-malleability game. So a puzzle for S looks like this. it's an encoding, a puzzle for SR using the underlying time lock puzzle. And he wants to generate one for S prime R prime, for some R prime where S prime is related to S. So what we can notice here is that the only way, at least intuitively, to generate this puzzle is to know the value of the random oracle on S prime and R prime. Because if you don't know this value, it's essentially uniformly random. So you basically have no chance of generating this puzzle without knowing this value. Without knowing S prime. So if you do know S prime, well, then you know something about S, because we sort of assume that S and S prime are related. But if you know something about S, that breaks the hiding of our time lock puzzle, which in turn will break the hiding of the underlying time lock puzzle. So that's just a little bit of intuition, but it's really, really using this circularity that we have. Okay, so using that, I'm going to sort of build up to our coin flipping protocol. So recall that what we want is coin flipping with an unbounded number of participants with up to n-1 corrupted parties, and we're going to have a public bulletin board. So our protocol is going to be exactly what I alluded to before, right? Each party is going to pick some random string. They're going to post it on the board in a time lock puzzle. And then after everyone has posted, or after some time threshold, they're going to post the solutions. Then if any solution was not posted, we'll solve the unopened puzzles, like we said before. And finally, the output will just be the XOR. This is just the direct extension from the two-party case to the multi-party case that I talked about before. So recall that we want these three properties. So optimistic efficiency says when everyone is honest, the protocol is really efficient. Fairness says no malicious party, even controlling n-1 players, can bias the output. And public verifiability says that anyone who comes later will be able to verify the output. So let's just look at how we get these three things. So for optimistic efficiency, this is exactly why we use a time lock puzzle instead of a commitment, right? If all these people are honest and post their puzzles and their openings, we don't need to solve any unopened puzzles. So nothing bad happens when there's no malicious parties. So that's optimistic efficiency. Okay, what about fairness? Well, I told you that to get fairness, we need non-malleability, right? That's the security property that says that all the SI values will be independent. But I told you that in the two-party case. And if you look at the multi-party case, it's actually just a little bit more complicated. So our time lock puzzles are non-malleable, right? So you get a time lock puzzle for S, you can't change it to one for related value S prime. But in the multi-party case, the adversary receives n puzzles. It doesn't just receive one. And we need it to hold that it can't take these n puzzles and then make any number of puzzles that are related to them, right? Because in the end of the day, the XOR of all of the values on the bulletin board, we want to be XORing independent values. So for multi-party coin flipping, we really need concurrent non-malleability, which just says that that if you get n values, you can't change them to n related values. So it turns out that this is actually impossible, at least in the sense where if you don't know how many people there are going to be in advance, you actually cannot achieve this. We show this in the paper. So to get around this, what we do is we actually introduce a weaker notion of non-malleability, and we show that we can still achieve it. So if you look at this protocol, let's call f the function that computes the output. So here it's just XOR. So it's actually okay if some of these SI values depend on each other. So like say the adversary is the last one to post, so he sees the first n-1 values and makes SN depend on them somehow by mauling these puzzles. That's actually okay as long as he doesn't change the value of the XOR. He doesn't bias the value of the XOR. So we introduced this notion called functional non-malleability, which basically says that given a bunch of time log puzzles, you can't change them into ones which noticeably change the output of this function on the values. And we show that this is actually possible. And the construction that I showed you earlier, going from a time log puzzle to a non-malleable one, it actually achieves this notion. So that's how we get fairness, through fully concurrent, which just means unbounded number of players, functional non-malleability. Okay, so the last one, public verifiability. I didn't really talk yet about how we get this, so let me just tell you quickly. What we know is that if everyone is honest, then everything is good, right? Everyone just computes the XOR, and given the bulletin board, you could easily recompute the XOR and know what the output is. But if there's an adversary that refuses to open their puzzle, an honest party is going to spend time opening it, then they know the opening and can compute the output. But what if someone else wants to know the output of this protocol? Like, what if we use this to, I don't know, pick a leader for some blockchain, some proof of stake blockchain, and then someone else wants to know later that the leader was chosen honestly. So in particular, if we just look at the two-party case again, if Alice posts her puzzle and then goes offline, Bob posts his puzzle, Bob reveals his puzzle, then Bob spends T time, which we're thinking of, sort of a long time, or it really depends on your application, but some significant amount of time, which makes the protocol less efficient. He spends this time to solve Alice's puzzle, and then he wants to tell Charlie the output. But Charlie needs to spend T time again to be convinced of this output. So to fix this, what we do is we introduce publicly verifiable time log puzzles, where when Bob is solving this puzzle, at the end of solving Alice's puzzle, he also gets a short proof that he can use to verify the solution. He can post it on the bulletin board, and then anyone that comes later will be able to verify it. So the transformation that I told you earlier, it preserves public verifiability. And we actually show how to construct a time log puzzle that's publicly verifiable. There are some caveats, but we rely on repeated squaring, and we can use it to get publicly verifiable multi-party coin flipping. So that's in a nutshell how we get these three desirable properties. So yes, that's basically it. So I'll just conclude. So in this work, we constructed non-malleable time log puzzles with no trusted setup. We introduced this notion of functional non-malleability, and we constructed publicly verifiable puzzles, time log puzzles. And then we combined these three ideas to get the first multi-party coin flipping protocols with these properties. And I guess one main open question here would just be to extend this to more applications. But with that, I'll conclude. So thanks so much for listening, and I'm happy to take any questions.
I guess one question is if you have intuition behind this functional non-malleability, like what is the property if like that disjoint between you can't say that someone can't make a construction based on somehow manipulating the set of the n other proofs that they have access to, but that their manipulations can't bias the output is the part that was less intuitive to me. I don't know if you've got any like thought of what that
means. Yeah, that's a great question. So here, let me just go back. Oh, that's fine. You can still see my screen, right?
Yes.
Okay, let me just go back to here. So this is the definition of concurrent non-malleability, right? So here's why concurrent non-malleability is impossible in a non-intuitive way. So this adversary, he receives these n puzzles, right? And let's say he's allowed to output as many puzzles as he wants. I put n on both sides, but actually he can, in an unbound setting, he can output as many as he wants. So what he can do, he can take the puzzles themselves and encode them as larger puzzles. So he will take the puzzle for S1 and create a puzzle for the puzzle of S1. and so on for the rest of these. And so the point here is that if he outputs those, they are clearly related to the inputs. Like a puzzle for S1 and S1 are related values. Like they could be distinguished by an unbounded adversary distinguisher. But that's kind of not, so it's an attack that prevents you from getting concurrent non-malleability. But if you did that in practice, or sorry, not in practice, like provably, if you did that, it wouldn't really make the output of the XOR biased, at least intuitively, because the puzzles themselves don't reveal anything. So that attack, it prevents you from getting concurrent non-malleability. But if you did that with functional non-malleability, you wouldn't change the you wouldn't be able to tell how you were changing the output of the XOR, in a sense. Does that make sense?
I think so. Like in my head, I'm thinking of this re-encapsulating a puzzle as like applying an additional set of squaring operations or something like that.
Yeah. And if you think of the RSW time lock puzzle, like this would be something like G to the 2 to the T plus S1. So the adversary would output G to the 2 to the T plus G to the 2 to the T plus S1. But actually, they would be for different G's and N's, depending on what the adversary did. But yeah, so that's the basic idea there.
Cool. Makes sense. I guess maybe my only other question is if you have thoughts about, are there like what your random oracle model is and what restrictions you have on there? So like, is there a way to have the participants themselves serve as that, or bootstrap this itself? And what is it that you're getting from having that as an external source of trust?
Yeah, so we definitely need the random oracle for our construction. We are in a slightly weaker model where we do allow the adversary to depend on the random oracle. It's called the auxiliary input random oracle model. I didn't really talk about it here, but yeah, so basically it in a sense, there's no setup that is independent of the adversary. So you don't have to assume that there's like let me say it a different way. If you're instantiating your random oracle with any old hash function, you can assume that the adversary has pre-processed the hash function and has like rainbow tables or whatever information about the hash function. But your question was more, could we replace that maybe by having the parties generate the setup or the oracle themselves? So we do actually partially do that, but we still rely on the random oracle to get our full protocol. Yeah, I mean, I think like in general, like generic techniques for removing random oracles, like you could, like there's nothing special that we need from a random oracle other than just being a random oracle. And like I said, we are in this model where the adversary can depend on it. So I think, yeah, like anything that you could do in other places, you could presumably do here.
Cool.
Thank you, Naomi. This was a great talk. To those of you watching on YouTube, please remember to like and subscribe. If you want to suggest a topic or a speaker, there are instructions on how to do that in the description. We'd also love to have you join our mailing list to receive quarterly newsletters, future talk announcements, and information on research funding opportunities from Protocol Labs. You can sign up for this mailing list in the footer at research.protocol.ai. Our next talk is next week, Tuesday, October 27th at 1600 UTC. Luca Muscarello from Cisco Systems. His talk will be on hybrid ICN. Thanks for joining, everyone. We'll see you next time.